Hello students, welcome to FW's platform for class 12 physics. Now we will consider a problem from electromagnetic induction. See the statement of the problem. See, a square loop of wire, this is a square loop of wire having negligible resistance. The wires are of negligible resistance. Side length of the wire is A. All sides are A. Has a capacitor C in the loop. The loop is kept symmetrically in the plane of two straight parallel wires. This is one wire, this is another wire. They are parallel to each other. The wires carry current I equal to I naught sin omega t in opposite direction. The current in this wire is downward direction. The current in this wire is in upward direction. Calculate the maximum value of the current in the loop. So that is the question. Now, first of all, in this square loop there is no source of electricity. There is only a passive circuit element which is a capacitor. Okay, and the currents are flowing in these two parallel wires, and this square loop is placed placed symmetrically between the wires. That means if it is A distance away from this wire, and if it is A distance away from second wire. Okay, now current quantity is given as I naught sin omega t. That means I is time dependent. Sometimes it is in this direction, sometimes it is in this direction. The moment at which the current in this wire is in downward direction, at that particular moment the current in the other wire is in the opposite direction. Now, because of current flow through these conductors, there will be a magnetic field produced in the region between the wires, and this magnetic field is time dependent because current itself is time dependent. And because of this magnetic field in this region, because of creation of magnetic field in this region, there will be a flux linkage through the square loop, and since the flux linkage, we can safely assume, if we call the flux linkage through the square loop as psi L, flux linkage will be time dependent because currents through the conductors are time dependent. As a consequence, the magnetic field produced by the currents will be time dependent, and therefore the flux linkage through the square loop will be time dependent. And since psi L is function of time, so you know, if there is a time dependent flux linkage to a loop, then there will be induced voltage in the loop, and that can be given as computed using this formula, Lenz's law. So there will be induced voltage in this loop because of time dependent flux linkage through the square loop. Now this is a circuit, you can say, having negligible resistance. There is only a condenser present, capacitor present in the loop. Entire induced voltage VL will fall across the condenser, and therefore I can write the charge in the condenser as Q equal to CVL. VL we have calculated using this, so from that I can calculate Q, which is CVL. And once we find Q, we can calculate the loop current, how much current is flowing in the loop. ILT is actually dQ dt, which is nothing but C dVL dt. So ILT, what is the current in the loop, that we can calculate, and since it is a function of time, once we get the expression for ILT, we can estimate what will be the maximum value of ILT. So we have discussed what is the origin of current flow in this, what is the reason of current flow in this square loop, and from that we can easily calculate what is the maximum value of the current in this loop. So this is the methodology using which we will solve the problem. So before we proceed, just to recapitulate one thing, you know, when there is a current carrying conductor, in the vicinity of the conductor or in the space surrounding the conductor. I should not say vicinity, everywhere in the region surrounding the conductor, in the space surrounding the conductor, magnetic field will be produced. And consider this conductor is of infinite length. Infinitely long straight wire carrying current I through it produces a magnetic field surrounding the space of the conductor, and at a point P, which is x distance away from the conductor, x is the perpendicular distance of P from the, if you drop a perpendicular for P on the conductor, this length is x. So at P, magnetic field Bx will be mu naught I by 2 pi x. Okay, I is the current in the conductor, mu naught is the free space permeability whose value is 4 pi into 10 to the power minus 7 Henry per meter. It can also be expressed as 4 pi into 10 to the power minus 7 Newton per ampere square. X is the distance and this is the magnitude of the magnetic field. What is the direction of magnetic field? You know that magnetic field direction can be found out using right hand rule. And magnetic field will be perpendicular to both x and I, direction of I. That means it will be perpendicular to the plane of this board. And in this case, it will be directed into the plane of the board. By thumb rule, if thumb directs the direction of current flow in the conductor at the point P, my fingers are curling towards or into the plane of the board, and therefore the magnetic field direction will be into the plane of the board. Applying right hand thumb rule, we can easily find out what will be the direction of magnetic field at point P due to the current carrying conductor carrying current I ampere. Okay, and units are, you know, it is Newton per ampere meter. Newton by ampere meter. Okay, so with this background, remember magnetic field's expression is mu naught I by 2 pi x. So with this background, let us try to solve this problem. So what is the expression of magnetic field? Just we have learned it is mu naught I by 2 pi x. So that we have learned Bx is mu naught I by 2 pi x. This is the basic formula, and thumb rule is the rule applying which you can find out what is the direction of magnetic field. Now, with reference to this diagram, consider a coordinate system like this. This is x-axis, assume. This is x-axis. This is x-axis. This, just a minute. This is x-axis and take y-axis along this direction. Okay, consider this point as origin of the coordinate system. This is x direction, this is y direction. Y direction is along the first wire. This is wire 1 and this is wire number 2. At a particular moment of time, wire 1 is carrying current along negative y direction, and at that moment the wire 2 is carrying current in the positive y direction. Now this point all these points P, Q, R, S, corners of the square. So coordinate of AS is how much? Is A0, because it is A distance away from y axis. Here it is R's coordinate is 2A 0, and this is Q's coordinate is 2A A, and this is AA. P's coordinate is AA. All right, A0, 2A0, 2AA. It is not 2A0, it is 2AA. And this is A. Now consider a point whose P, say this point you call say T, whose coordinate is xy. Okay, so consider a point xy in this plane inside the loop. Okay, so this point is xy point, and x is definitely greater than a but less than 2a, greater than equal to a but less than equal to 2a, and y is definitely greater than 0 but less than equal to a, greater than equal to 0, less than equal to a. So I am taking a point xy within the loop, and surrounding this point xy, consider a small rectangular area having area of cross section dx dy. That means this distance, it is dx, and this distance, it is dy. Okay, so just imagine a small area dx, shaded area dx dy surrounding the point xy. That means dx dy is a small rectangular elementary area. Dx dy both are very small quantities. So rectangular area dx dy is surrounding the point xy, and dx dy is so small that we can assume that magnetic field produced due to the current carrying conductors through this rectangular area dx dy is uniform. Now what is the magnetic field Bxy at the point xy? Let us calculate that. So Bxy, which at this point is, see here it has no role of y, it only depends on x coordinate of the point, and it is simply mu naught I by 2 pi x z cap. So this is the field due to wire 1. Field due to wire 1. Wire 1 is this one. So see, current is flowing in this direction, and at this point the magnetic field will be coming out of the plane of the board, and we are considering a coordinate system xyz. This is x-axis, this is y-axis, and this is z-axis. Z-axis is perpendicular to the plane of the board. X-axis is this line, y-axis is this line, and z-axis is perpendicular to the plane of the board. And because of the wire 1, where current is flowing in this direction, downward direction, magnetic field at xy is coming out of the plane of the board, and therefore I am writing it is mu naught I by 2 pi x z cap. It is the magnetic field. Okay, field due to wire 1. Now we have to calculate the magnetic field at xy point due to wire 2. So it will be how much? Mu naught I. Here again the current is I, mu naught by 2 pi. And what is the distance of the xy point from this conductor? So total distance is 3a, 3a minus x. So it is 3a minus x. And here again you see the current is flowing in this direction, positive y direction. So magnetic field at this point, from the direction of curling of your fingers, you can easily write that the magnetic field at xy point due to current in wire 2 will be in the positive z direction. Okay, so both magnetic fields due to wire 1 and wire 2 at the point xy, they are in the same direction, so they are simply added, and this is field due to wire 2. Okay, so these two fields, this is the contribution of wire 1, this is the contribution of wire 2, both are in the same direction, that's why they are added, both are in positive z direction. So this is the expression of magnetic field. So I can write the magnitude of magnetic field or vector dxy at the point xy as mu naught I by 2 pi 1 by x plus 1 by 3a minus x z cap. Up to this there is no doubt, I believe. Okay. Now next task is to find the flux linkage through the square loop. Square loop PQRS. Now for that, what we will do, if we know that through a area there is a uniform magnetic field, and if the magnetic field is perpendicular to the square or area, then we can easily calculate the flux as area multiplied by the magnitude of the magnetic field. But here you see at different points inside the square loop, magnetic fields are of different magnitude. But let us consider this small area, this particular area whose thickness is dx, width is dy, and since dx dy are very small, we can assume that through this area the magnetic field will be uniform, and that value of magnetic field will be given by this particular expression. So what is the flux linkage through this small rectangular area dx dy? That if we call it d psi l, differential flux through the area, then it is d psi l through the rectangular area surrounding the point xy is nothing but bxy multiplied by dx dy. This is clear. This is the elementary flux linkage through this particular area dx dy, which is d psi xy, d psi l xy. L represents loop, bxy dx dy. Therefore, what is the total flux linkage through the loop? So I have to sum up all these elementary fluxes. So it is nothing but integration of bxy dx dy, and you have to carefully choose the limits of integration. For the entire loop, x varies from a to 2a. So x varies from a to 2a, whereas y varies from 0 to a. Alright, so it is how much? It is y equal to 0 to a. X equal to a to 2a. bxy, if I write mu naught I by 2 pi 1 by x plus 1 by 3a minus x dx dy. So I can write these quantities independent of y. So I write as y equal to 0 to a dy, x equal to a to 2a, then 1 by x plus 1 by 3a minus x dx, and whole thing multiplied by mu naught I by 2 pi. So it is how much? mu naught I by 2 pi a x equal to a to 2a 1 by x plus 1 by 3a minus x dx. So what is this integral? It is just, let us evaluate this particular integral. Carefully note. So integral 1 by 3a minus x dx. How to calculate that? Let u equal to 3a minus x. You know u substitution technique in integration. So du is equal to negative of dx. So I can write this integral as negative du divided by u. So it is negative ln u. So it is negative ln 3a minus x. Okay. So this integral is actually mu naught I a by 2 pi. First integral is nothing but ln x, and second integral is negative ln 3a minus x, and limits of integrals are a to 2a. So we have to evaluate this quantity. So what is that? So for that, let me remove this part. So how much it is? It is just check. So psi L is equal to, this is psi L expression for psi L, mu naught I a by 2 pi. Please follow the steps. So it is ln 2a minus ln a minus ln a plus ln 2a. So it is how much? Mu naught I a by 2 pi 2 ln 2a minus ln a. So this cancellation of 2's from numerator and denominator. So it is mu naught I a by pi ln 2. Mu naught I a by pi ln 2, because ln 2a by a is ln 2. So we have got the expression for flux linkage through the loop. So we are almost through. So we could calculate what is the flux linkage through the square loop. So we can write the expression for psi L, flux linkage through the loop, as psi L equal to mu naught a ln 2 divided by pi. I is I naught sin omega t. I naught sin omega t. So this is the expression for flux linkage through the square loop. Mu naught I a by pi ln 2. Okay. Now we'll proceed further. So once we know the flux linkage, what is the induced voltage in the loop, that you can easily calculate using Lenge's law. So Lenge's law gives VL, which is nothing but the induced voltage in the loop, can be expressed as negative of d psi dt. So I will write VL as minus d psi dt. VL equal to minus d psi L dt. So it is minus mu naught A ln 2 I naught cos omega t, and there will be one omega over here by pi. So mu naught A ln 2 I naught omega cos omega t by pi. This is VL. Once the induced voltage in the loop could be calculated, then what is the charge in the capacitor? Q equal to CVL, which is minus mu naught A ln 2 I naught omega square C cosine omega t by pi. See, this is the capacitance of the capacitor. So once we know Q, then dq dt gives you the current in the loop IL at any moment t, which is what? dq dt is actually C dVL dt. Okay, so Q's expression we have found. So dq dt is how much? So IL t is, there is a cos function, so when differentiated it gives a negative sign, so I get ultimately a positive sign, mu naught A ln 2 I naught so here actually I should not put omega square, it is omega only, it is omega. Q equal to C VL, mu naught multiplied this quantity multiplied by C, mu naught A ln 2 I naught omega C cos omega t by pi. So it is mu naught A ln 2 I naught omega square here C sin omega t divided by pi. So this is the expression for loop current, mu naught A omega square I naught C ln 2 sin omega t by pi, or I can write it is as A omega square mu naught I naught then C ln 2 by pi multiplied by sin omega t. So what is the maximum value of ILT? ILT's expression is this much, which is time dependent and it depends on a sin omega t function, and you know sin omega t is a time dependent function, its value lies in the range -1 to +1 always. So maximum value of sin omega t is +1. So when this quantity becomes +1, I get the maximum value of IL. So IL max will be A omega square mu naught I naught C ln 2 divided by pi. A omega square mu naught I naught C ln 2 by pi. So this is the expression for maximum value of the current flowing in the loop. Okay, you can find the direction of current flow or VL, current flow, applying second part of Lenz's law. You can work it out. If you have any doubt, please revert back to us. So I think you have understood the steps involved in solving the problem. We started with how much magnetic field is produced due to a current carrying conductor. Then we found what is the direction of magnetic field and direction and magnitude of magnetic field at the point xy inside the loop. From that we could calculate the differential flux through the area dxy. Then we calculated the total flux linkage to the square loop by double integration, integrating over x and y. Then once the total flux linkage could be found out, we could find the induced voltage in the loop using Lenz's law, VL equal to minus d psi L dt. Once VL is found, then what is the charge held by the capacitor C? That you could find using Q equal to C VL. So just multiplying VL by C, we could find the expression for charge. Once the expression for charge could be found, we could find the loop current by differentiating Q with respect to T. So this is the loop current, which is a function involving sine omega t. So ILT becomes maximum when sine omega t is maximum. Maximum value of sine omega t is +1. Therefore, IL max is this much. So many concepts are involved in solving this problem. If you understand this problem, then many concepts will be clear. I hope you have understood and followed the steps involved. So if you have any doubt, you are free to revert back to us. You can ask any questions. We will try to clarify those doubts further. So thank you for your listening. Thank you very much.